emitted or absorbed by the electron, has associated with it a particular frequency when the EMR, when that same EMR is behaving as a wave. And when we talk about line spectra, we often talk about the frequencies of the individual lines, okay, or the wavelengths of the individual lines in line spectra, and that frequency corresponds to one of those lines. Does that make sense? Clear it up? Yep.
He said he could not explain why.
But yeah, he can't explain why the electrons are absorbing these photons and not other photons, or absorbing or emitting these photons and not other photons. He didn't really explain that. So he did not give us a full explanation of line spectra. I don't know about you, but I'm not going to be happy until I know, well, why these photons and not the other photons. Okay? When we have someone who can finally answer that for me, then I'm going to be good. Okay? But I have a much better idea now of what a line spectra involves, what the mechanism is involved. And it has to do with the electron absorbing and emitting these photons. So it gave us a better picture of what's going on. Carrie, good? Questions? Okie doke, in that case, number 12, why was classical physics stumped by the photoelectric effect? How come? Eric?
They were stumped by this because light of light of frequency should carry increasing energy as the intensity of the light increases to help electrons accumulate enough energy to break free from the pull of the nucleus. So like a bright green light should have more total energy.
It does.
Than a dim yellow light, but it doesn't. But even a dim yellow light would allow electrons to break free from a metal that has a...
You're confusing a bunch of people is what Shaitan is about to try to tell you. Yeah, you used green and then you went to a lower frequency yellow saying that, yeah, you see how that sort of like starts to confuse a bunch of people. Okay, but he hit the main point, which is classical physicists were stumped because light of any frequency should be able to provide the energy the electron needs to escape the pull of the nucleus. Light of any frequency, so long as you make it bright enough. Okay, you should be able to provide the energy the electron needs to escape the pull of the nucleus using any frequency. You just have to compensate for the lower frequency ones by making it brighter. Does that make sense, guys? Joe? Maria, make sense?
Yeah.
Okay. And that doesn't happen. That's why they were stumped. I mean, it should work, but that doesn't work. Questions? Okie doke, in that case, number 14, or rather 13, how did Einstein explain the photoelectric effect? So how did he explain it? Kyle?
He said that as you increase the intensity of the light, the total energy increased, but that didn't affect the energy of individual photons, it just increased the number of them.
Okay. And since the electron can only absorb one photon at a time, and if it does, it has to do something immediately with it, sending down more photons is not going to help if the energy of the photon isn't sufficient to begin with. Ryan, make sense? Matthew, we good? Ada? Questions? Abby, okay? All right, in 15, you had to determine if the Planck's constant was given to you, what's the energy of the photon associated with a wave having a wavelength of 500 nanometers? So, real quickly, let's see that we can knock this one off. So we wanted to find the energy of the photon.
You skipped one.
Oh, shoot, I was so eager to get to the problem. Okay, fine. What was significant about Einstein's explanation of the photoelectric effect? Real quickly, by being able to explain the physical phenomena that stumped classical theory, it lent great credibility to quantum theory, and it's why it was accepted. Okay? Remember, you know the deal. You've heard this before. When do we accept a new theory? When it does everything the old theory could do, but does something the old theory could not do. Okay? This new theory of light, this quantum theory, the fact that it could explain a physical phenomena that classical theory could not explain, specifically the photoelectric effect, lent great credibility to it, and that's why it was accepted. They want you to find the energy of the photon. Easy. All you need is the frequency, but they didn't give you the frequency. So how can with the frequency? Well, C equals lambda times nu will give us a way of getting the frequency. All you have to know is the wavelength. Did they give us a wavelength? they did this time. Of course, I could give you 1 over lambda is equal to 10, 9, 6, 7, 8 times 1 over n sub 1 squared minus 1 over n sub 2 squared. So I could ask you, what is the energy of the photon associated with the second line of the Lyman series? So then you have to get the wavelength. Once you get the wavelength, then you have to get the frequency. Once you get the frequency, then you got to get the energy of the photon. And then let's turn it into matter
Yeah.
and see how much matter we can get.
That's my type.
Would you do that on the test, Mrs. Swan? Yeah, that's easy. That's easy. That's not hard. You guys should be able to do that. As it so happens, in this particular problem, I didn't make you go through and solve the Rydberg equation again because I gave you the wavelength, so you could start right here. And they weren't asking for the mass that we could produce by converting it into matter, so we're not going to be using equals squared. That means we're just using these two formulas. Now, to use this again, this is 3 times 10 to the 8th. This is meters per second. So that means our wavelength also has to be in meters again. So we need to take the 500 nanometers, and we have to change that. 10 to the 9th nanometers to 1 meter. That means I'm dealing with 5 times 10 to the negative 7th meters. That's what I want to put up over here. 5 times 10 to the negative 7th. And then I'll solve for frequency. When I do that, frequency turns out to be, what do you get, Matthew?
6.00 times 10 to the 16th.
16th what, Hunter?
Hertz.
Hertz, or seconds to the minus 1, that's right. Questions? Yep,
I got to the 14th.
that sounds actually better. That sounds more reasonable from what I recollect, based on the nanometer range. Did you do this step right here?
Yeah.
Okay, and you got 10 to the negative 7th?
Nope.
What did you get for your wavelength?
Oh, I converted the speed of light into nanometers.
Oh my God. Okay. I mean, you could do that. What'd you get as the speed of light in nanometers per second?
3 times 10 to the 17th.
Yeah, that's right. So you did 3 times 10 to the 17th is equal to 5 times 10 to the 500 rather times nu.
Yeah.
And so when you did this, how did you solve for your frequency?
I just divided it by 500.
Okay, and then you got to the 6 times 10 to the 14th, I mean, to the 15th? 16th, what'd you get?
Yeah, 16.
Can you see how 3 times 10 to the 17, and this is 5 times 10 to the 2, can you see how already that doesn't make sense?
Yeah.
Okay, so you use your calculator to do this, or you did it in your head?
Calculator.
Okay, sometimes that happens. You hit the wrong button. That's why you show your work. Okay, so this is a classic example. Why you want to show me your work. Show the value, the formula, plug in the values, give the final solution with the units, because you might hit the wrong button, like Matthew did, and I dock you a point for hitting the wrong button. As long as the math is there, I'm okay with that. Once you have the frequency, then we can go ahead and plug it in here. So E is equal to 6.63 times 10 to the negative 34th. Again, I'll give you Planck's constant on the test. You don't have to have that memorized. This is 6 times 10 to the 14th. When we solve, Carrie, what do you wind up with?
3.978 times 10 to the negative 19 joules.
10 to the negative what?
19th.
19th joules?
Yeah.
Okay. You want to put it in 3 or 4 sig figs is your final answer. Questions? Abby? You sure?
Yeah,
Yeah.
I just keep on like not understanding that I need to do more than what I'm doing. Like I thought thought that it was frequency in this one, and then for like for one of the other ones, I didn't change it to meters. So.
And I'm all about I'm all over that type of stuff. That's how you lose bunches of points.
Yeah.
Okay, so that's why we're going through this now to make sure that you know what you're doing. Questions? Okay, Einstein's equation, of course, is E equals mc squared. All right, Anna, you're up. What do the letters stand for?
Energy.
Uh-huh.
E stands for energy. M stands for mass, and C stands for speed of light.
Okay, good. And what's its significance? What's this imply? What's the big deal about this?
It says that mass can be converted to energy, and energy can be converted into mass.
That would get you about a third of the points, maybe. So we need more. Okay, how is it possible, Ada, that I can convert matter into energy and energy into matter? How is that possible? I can convert these paper towels into light? Theoretically, I can. Now, you might be saying, good luck with that. Well, right, because we don't have the technology, but Einstein's equation, this is what I want you to understand. Einstein's equation is making that claim. The world is that upside down. I mean, the fact that your desk and light are essentially different forms of the same thing, that's what you need to come out with. You want to lead off with that, okay? You're not wrong when you say we can convert mass or matter into energy and energy to matter, okay?
It's not all of it.
No, my point is, though, is that sort of sidesteps the more amazing statement, which is matter and energy are just different forms of the same thing. You understand? Now, because of the different forms of the same thing, that's why we can convert them, okay? But you want to lead off. Your first opening statement should be this, that this equation implies that matter and energy are just different forms of the same thing, or mass, I should say, technically. Mass and energy are just different forms of the same thing. Mass and energy are just different forms of the same thing. Okay, this again implies that mass and energy are just different forms of the same thing. Now, because of that, here's what we want to say. You said, and therefore we can convert matter into energy, or mass into energy, or energy into mass. That's fine, but there's a specific ratio. So you want to say, okay, specifically. So our next statement would be specifically, a tiny amount of matter can be converted into a tremendous amount of energy, and a tremendous amount of energy can be converted into a tiny amount of matter. You need that level of detail in your reply. So again, one more time. This equation implies that matter, or mass, and energy are just different forms of the same thing, and consequently, a tiny amount of matter can be converted into a tremendous amount of energy, and a tremendous amount of energy can be converted into a tiny amount of matter. You are not allowed to say vice versa. You can't say, I'll tell you what. I had a student in Orange Camp said, and vice versa, Mr. Swan. And I said, a tiny amount of matter can be converted into a tremendous amount of energy, and vice versa. I said, what do you mean by that? Well, you can also take a tiny amount of energy and convert it into a tremendous amount of matter. So from that point on, I no longer allow vice versa. Okay? All right, we'll finish up with the rest of this tomorrow, guys. See ya. Joe, don't forget your phone. Again, tell Mary I hope she feels better. Did you take her soup?
I was going to.
Oh, bad Joe. Bad.
His mom made soup, which is why I didn't take it.
Fine. Then follow up with the cookies. What? You're gonna go, Jess? Okay. Okay. I'm sorry to put you on the spot like that. I just don't really have a choice.
It was mainly my fault.
Okay. All right.
Oh.
What?
Yeah. Mr. Swan, there is a math competition.
coming up when
Yeah.